Okay, so superposition is this idea that you can take a problem that has a whole bunch of non-homogeneous elements in it and break it apart into subproblems that each separately deal with one or a couple of the non-homogeneous parts of the original problem. So we'll talk about it here, and you'll have to use it for your homework, I think. So here's a problem that superposition would be required to solve. So we have this this computational domain over here. So we have the same partial differential equation. Our boundary conditions are all four non-homogeneous, right? We have a temperature boundary condition on this side, a different temperature boundary condition over here, a heat flux down here, and convection to some temperature up on the top. So this is the mathematical statement of the problem. And all four boundary conditions are not homogeneous. I can get one homogeneous boundary condition by doing the same kind of transformation that we just did, right? So I could solve for theta, where theta is T minus TL, for example, and that would turn this boundary condition into a homogeneous one, but the other three still wouldn't be. And so I still wouldn't have a homogeneous direction, right? So that really wouldn't help me with this problem. So I'm forced to use superposition for this problem. What superposition does is it breaks the problem into two parts, right? A T1 problem and a T2 problem. And what you're going to do then is you're going to use one of these two problems to deal with the non-homogeneous boundaries in the y direction. So the T1 problem will deal with this boundary condition and this boundary condition, but it'll replace these two boundary conditions with their homogeneous equivalents. So that'll be a problem then that is solvable using separation of variables. And then T2 is going to deal with the non-homogeneous boundaries in the x condition, right? So it'll deal with this boundary condition and this boundary condition, but it will replace these boundary conditions with their homogeneous equivalents, right? So again, that one would be solvable using separation of variables. And then what you'll see is that if you solve T1 and T2 separately, you can add those two solutions up and you get the solution to the original problem. So it's kind of a turn the crank method, right? It's not complicated. You do have to know what the homogeneous version of a non-homogeneous boundary condition is, and that's not too difficult to grasp. If I have a set temperature boundary condition, then the homogeneous equivalent of that is that set temperature is equal to 0. That's pretty obvious. If I have a set heat flux boundary condition like I do here, then the homogeneous boundary condition that is equivalent to this is the heat flux is equal to 0. So that's an adiabatic boundary. If I have, like I do here, a convection boundary condition, the homogeneous equivalent of this one is still convection, but to a T infinity that's equal to 0, right? So to a fluid temperature of 0. So those are the replacements that I'll make. When I'm solving the T1 problem, I'm going to replace the non-homogeneous boundary conditions in X, so these two guys, with a 0 temperature and a 0 temperature, right? Because that's the homogeneous equivalent. So when I'm solving the T2 problem, I will replace the non-homogeneous boundary conditions in Y, these two guys, with, in this case over here, an adiabatic boundary at Y equals 0, and over here a convection boundary but with a fluid temperature of 0, right? So that's what this looks like. Here's my original problem. Here's the problem statement, right? I can't solve this one using separation of variables. I'm going to split it into a T1 problem where I replace this temperature boundary condition here with 0 temperature, and this one here was 0. So these are my two boundary, this should be 0 right here. Wasn't careful enough. This guy right here should be 0. So I've replaced these two boundary conditions with their homogeneous equivalents, and then I just leave these non-homogeneous boundary conditions here and here and deal with them. So this is a problem I can use separation of variables to solve, right? X would be my homogeneous direction. We'd go through the entire process and I'd get a solution at the end. And then I have to deal with these two boundary conditions, this temperature and this temperature. So I deal with that using my T2 problem. So my T2 problem keeps these two non-homogeneous boundaries, right? Those are the same as they were. But now I replace the boundary condition down here at y equals 0 with its homogeneous equivalent, which is adiabatic. That's what this is. And I replace the boundary condition up here at y equals h with its homogeneous boundary condition, which is convection still, but to a 0 temperature, right? That's what this is. This one also is solvable using separation of variables. So, at this point, I just move forward using separation of variables in the normal way. I get a T1 solution, I get a T2 solution, and then my solution to the original problem is just T is equal to T1 plus T2. Right? And if you take this substitution and you put it into this original problem, what you should see is that if you solved this problem and this problem correctly, every single condition over here, every boundary condition and the differential equation will be satisfied. So for example, if I take this substitution and I substitute it into my original boundary condition, which I did here, right, then I get d squared t1 dx squared plus d squared t1 dy squared plus d squared t2 dx squared plus d squared t2 dy squared is equal to 0. Well, this being equal to 0 is what I used for my T1 problem. This being equal to 0 is what I used for my T2 problem, so sure, that's going to work, right? Same for any of these boundary conditions. Let's take this boundary condition here. The boundary condition is the temperature at x equals 0 is equal to T sub L, right? So if I plug this into here, I get that T1 at x equals 0 plus T2 at x equals 0 has to be equal to T sub L. Well, T1 at x equals 0, if I look up here, is equal to 0. And then T2 at x equals 0 equal TL, that is the boundary condition that I was using over here. So that will be satisfied. Same thing, let's do one more. This is the heat flux boundary condition. This is, the heat flux has to be equal to minus k dt dy. So if I plug this into here, it would say the heat flux has to be equal to minus k dt1 dy at y equals 0, minus k dt2 dy at y equals 0. Well, this part right here, if I go look up here, that's equal to 0, right? That is the boundary condition I used for T2. And this part right here, that's exactly the boundary condition I used for T1, right? So every boundary condition will be satisfied, and the partial differential equation is satisfied, therefore the problem is satisfied. And that's superposition, right? You just sort of are able, using this technique, to solve problems that have basically as many non-homogeneous boundary conditions as you want by dividing them into smaller problems that are solvable with separation of variables. Okay, so that's pretty much it for separation of variables. We went through the basic process in some detail, and then this lecture hopefully has sort of caught you up to the point where you can solve more realistic problems, which is important if you actually want to use this to solve problems that you might come across, as a working engineer doing interesting things.